So the title for this section of our notes is hybridization. I'm curious if you remember or if you were even using that word last year in biology class. You remember doing hybrid crosses with Punnett squares? Yeah, like capital T's and lowercase t's, and you put them in the squares to figure out what the possible offspring of whatever it was you're looking at could be, what those genetic possibilities were. It was not something that ever told you what you would get. It just told you what the possibilities were. Well, we use it in chemistry in a very similar way. In biology, it's the idea of mixing things to see what your new generation could be. We're going to be mixing some things to match what nature does as far as we can tell. Now, I'm going to begin with something you don't need to add to your notes, but I do want you to take a look at. No, I'm not going to, because for whatever reason, it is not changing. Are you going to work now? Yay, now it works. Okay. This is nothing to add to your notes. I'll get to something to write in just a minute. But I want you to see, I showed this once last week and said I wouldn't require you to actually be able to figure it out, and I'm still holding to that. I just want you to see what's going on. For this compound CH4 to form, we see that carbon is starting with 4 orbitals in its valence level, and each of those orbitals has an empty spot, and that's why it takes 4 hydrogens. Every one of those hydrogens electrons pairs up with one of the carbon's electrons, and that makes us have those 4 bonds. My question for you as we look at this slide is, notice how carbon's using one of its s orbitals and 3 p orbitals. Which of those becomes which of these bonds over here in the picture? The S is on top. I like that. Any other guesses? Do you have any way of telling? Any way to know which ones of those is the S? No, we can't see with our little plastic model, can we? Okay, so scientists, of course, are like, well, we want to know which one is the S. Well, okay, so we're going to take it to a lab. We're going to put in a machine and we're going to measure. And it turns out we can't tell either. Even in the machine, we can't tell which one is the S and which others are from the P. They all look the same. So that's the idea with hybridization. So now you're ready to put down your definition of hybridization. Hybridization is the central atom mixing the orbitals it needs to hold the number of single bonds and lone pairs. It mixes them to make something new, just like your Punnett squares last year showed you how the genes could mix for the new offspring. Please take your earbuds out. So our first of 2 topics today is hybridization. Hybridization is that mixing of those various orbitals to hold whatever it is that needs to be held. And it mixes so well, we can't tell any difference between them. Now, the good news is it turns out to figure out the Hybridization is super easy. You might want to make note in your notes that the hybridization will equal the CP number. Now, I'm showing you the possibilities down here on the screen. You don't need to write that in your notes. We're going to go through your chart and write those on your chart. But if hybridization happens to hold bonds and lone pairs, and CP is a count of bonds and lone pairs, it's very convenient that the hybridization will match your CP. Okay, so it looks like everyone's got this down. So let's go to your Vesper chart. On your Vesper chart, you've added to the left a column that says hybridization, and it works really well to add it to the left, because what's the column right next to it? CP. And what did I just say? Hybridization will match your CP number. So that's why I like adding it here on the left and left you space here on the left to add it in. So the first one in our chart is a 2, a CP of 2. How many orbitals does it take to hold 2 pairs? Well, the answer is 2. What letters would those orbitals be? First orbital is an s orbital, right? You remember doing 1s, 2, 2s2, 2p6, 3s2. Okay, so we start with an s. So our first orbital is an s, but that only holds 1 pair. We need to hold a second pair. So after s, where do we go? P. And we only need 1 P because we're only holding 2 pairs total. So notice how I count it out, SP. So as you can see on the bottom left of the screen, we call that SP hybridization. So in your chart, right next to the 2, you want to write SP. It is SP hybridized. And again, it looks just like you see right here on my screen. That's why I listed them so you could see how we write them. Any element with a central pair count of 2, that center atom has hybridized an S and a P, and we call it SP hybridization. Now the very next line's a 3, but all the 3s are the same because they're all 3. What would it take to hold 3 pairs? Well, again, we start with S, and then after S, we go to P. Do you remember how many boxes there were that had P? S was 1 box and P was 3. We have up to 3 P's, but I only need to hold 3 pairs total. So I need 1 S and how many P's to get up to 3? 2. Notice how it adds up. That's exactly how it works. So anything that has a central pairs of 3 would be SP2 hybridized. So write that in on your chart. Anything that starts with that CP of 3, right next to that CP of 3 every time, SP2. Now remember, just like in math class, when we don't see an exponent, there's a 1 there. So you literally can add the exponents and go, oh, 1 plus 2 is 3, and this is CP3. That's enough. So all the 3s are SP2 hybridized. Next up, we get a central pairs of 4. So what's it going to take to hold 4 pairs? 1 S, because we always start with S. And then to get up to 4, I need 3 more P's, don't I? That is SP3 hybridized. So on your chart, everywhere that you have a CP of 4, you want to write SP3. SP3 hybridization. Again, remembering that the S has a 1 with it, 1 plus 3 is 4, and that gets you your central pairs number. So knowing your central pairs number, you can just add up until you get that number. Now notice what happens when we get to 5. I have it up on the screen already. 1s, 3 p's, but now I'm out of p's. So what sublevel comes after p? D. So it takes 1d. So everything, all of those that start with the CP of 5, you would have sp3d hybridization. So that the 1s, the 3p, and the 1d all add up to 5. So in the case of sulfur or phosphorus, where they're holding 5 bonds around themselves, bonding to other elements, those elements are blending 1s orbital, 3p orbitals, and even 1d orbital in order to hold all that together. It's something only elements in row 3 and beyond can do, because D doesn't appear till the 3rd energy level. And then we do have some elements that can even go up to 6. And so we add just one more D into the mix to go up to 6. So anything on your paper starting with a CP of 6 is sp3d, 2. 1s, 3p, I'm up to 4, 2 Ds, now I'm up to 6. Now that's usually as far as most natural elements will go. But I was just getting my master's degree at UNT, several of my friends in the classes were working in lab, trying to see if they could change what nature did. Several of them were seeing, could we even get some hybridization going with F orbitals? Well, if you go with elements in energy level 4 and beyond, yes, we could. Is it the normal thing nature's going to do? No. But we are mankind and we can bend nature to our will or something. But these are the normal hybridizations. So as you get to your practice later, you're going to start seeing, I put in a little hybridization drop down. And so you're going to look at your CP and you're going to drop down to whatever hybridization adds up to your CP, and that's all there is to it. So it's a recognition that the atoms blend together their orbitals. Even though you think to get 6 pairs, one of those pairs is stuck in an S, 3 of them are stuck in P's, and 2 of them are stuck in D's. We can't tell any difference. The atom blends them all together into new kind of orbitals, and so we just call those new orbitals sp3d2. So that's hybridization. It matches your CP number. It just states which orbitals are involved to hold it all together. Any questions about that? Okay, before we get to our second topic for today, I do want to show you this. Now, this is nothing you need to write down into your notes. I just want you to watch. I wanted to show you what to do when there's more than one atom in the center of a molecule. Many of you are likely going to want to consider taking organic chemistry either your junior or senior year, especially if you know you're going into a major that's heavy in chemistry. You would certainly have benefit of taking organic chemistry with Miss Keith here before you take it again in college. It'll make it way easier to do well in college, having seen it before. So to help her out and to stress the point of how much we have done that still works, I want to show you what's going to happen when we have multi-center molecules. So I'm going to pick a simple molecule, C2H6, and I'm going to do the same steps we've been doing. 4 for each carbon. Each hydrogen is worth 1, so I'm going to add 6. So we get 14. So in my picture, I need to show 7 pairs. Now here's why it's different than what we've done. Normally, if you had carbon, you'd put the carbon in the middle and the hydrogens around the outside. But I have 2 carbons. So I'm going to put 2 carbons in the middle with hydrogen around the outside. And so I'm going to draw the bonds. I'm going to draw the hydrogens in. I need to show 7 pairs. How many bonds am I showing in that picture? It works out, right? Yeah. Okay, so I need to show 7 bonds, or 7 pairs, sorry, and I'm showing 7 bonds. I'm done. That's my picture. Different than we've done, and I certainly wouldn't hold you to doing that like on the test. But that is the way that we take our steps and we work it out. Same steps work, even when you have more than one element in the center. Now watch what happens when I do this. Now this is slightly different. This is C2H4. I still have 2 carbons, but now I only have 4 hydrogens. So I'm going to show 6 pairs, 2 carbons in the middle. Now it's 4 hydrogens, so I'm going to stick hydrogens on each side. And that's only showing 5 pairs. I have 6 pairs to show, so just like normal, we do a lone pair. And for reference, I'm going to call this carbon 1, and this is carbon 2. Now, carbon 1's okay, but what do you notice about carbon 2? It's a synopsis element. It needs to have an octet. Does carbon 2 have an octet? No. So how do we fix that? Same steps we've done earlier. We change a lone pair into a multiple bond. Does that fix up carbon 2? Yeah. And so we see now, yes, this carbon has an octet, and this carbon still has an octet. Both carbons being synopsis elements are good. So that's how we would know that compound has that double bond in it. Same steps we've done, we're just applying it to a different situation. And that's what I want you to see. These steps we've learned, if you take organic chemistry, will still serve you very well. It's the basics of what they do in organic chemistry. Now I have 2 carbons and only 2 hydrogens. So I'm only going to show 5 pairs. 2 carbons, 2 hydrogens. I got some lone pairs, so I'll put them there. I'm going to label it carbon 1, carbon 2. Carbon 1's good. What about carbon 2? Yeah, it doesn't have the octet. Okay, let's fix that. Let's erase and make a double bond. Does that fix it up? No. Okay, well, let's keep going then. Let's erase and make another bond. Does that take care of it? Yeah, and that's how I know it's a triple bond in the middle. So the same steps we've been doing work still, even to larger molecules with more than one center. Last one I want to show you, just because it's kind of fun. 2 carbons, 4 hydrogens, 2 oxygens. I believe that's 24. So carbon to 3 hydrogens, carbon, oxygen, and it gets an octet, to an oxygen, to a hydrogen, it gets an octet. Is everything good and set up? Which one? The carbon on the right's not. Okay, so let's fix it up. I mean, that's 12. I can't do anything more, but let's erase a lone pair and we'll make another bond. And now it's good, isn't it? Yeah, same steps we've been doing, so apply. Now, if I had just given you those elements and asked you to draw it, would your drawing have looked anything like mine? No, that's why there's stuff to be taught in organic chemistry. A lot of organic chemistry is figuring out what's where. In fact, that's why NMR spectra exists. So even if we don't know what's where, we have a way to figure out what's where. So there's still plenty to be learned in organic chemistry, but when it comes to making the structures, even a structure like my favorite compound, caffeine, if I were to take this one element at a time, even with the rings, the steps that we have gone through this unit would still apply and would eventually get me to that structure. Now, is that nearly as easy as we've been doing? No, but these steps are still the foundational ones, still work even for organic compounds. So I wanted you to see that in case in a year or two you take Miss Keith's organic chemistry, you have the idea that what we are learning definitely transfers over and is still in use in that class. Now we do have one final topic that is going to be in your notes today. So one final topic today to put in your notes. If you like titles for your topics in your notes, you can title this Formal Charge. So we looked at hybridization and we filled in the column and completed our VSEPR chart. And by now our VSEPR chart is done. So if that's good news, we have filled in all of the VSEPR chart we need to fill in. Formal charge, this new topic, is how we're going to decide that the place we put the multiple bond is the correct place to put it. So I'll get to that in just a minute, but that's what formal charge is going to do it for us. So title is formal charge. Here's how we figure out a formal charge, and then we'll do several examples. I'm sure you'll see it's easy but different. And then we'll practice it from there. So I'm going to be quiet for a few minutes. You want to get down the 3 steps for finding formal charge. You want these 3 bullet points to know when you compare what the best case scenario is going to be for the situation. And then we're going to practice that. And I even want to prelude our lab, which next time I see you, so what's that going to be, Wednesday, we're going to be doing a little lab along with our intermolecular forces. So classroom students here get to actually physically do the lab. It'll be oh so much fun. I'm sure you'll enjoy it. If not, you're going to pretend you're going to enjoy it anyway. And online students, you'll have the opportunity to see how the lab works as well before we leave today. Formal charge is what chemists have come up with to determine what the best way to draw structures are when there possibly could be more than one good way to draw it. It's a way to like prove it, if you will. It certainly is a way to show which one's most likely going to match what nature does with that compound. Takes 3 steps for every element. They are very different than any of our other steps for anything we've done. So please notice, very different steps. We are taking our valence electrons from the periodic table, but we're subtracting for every bond that touches that particular element. So again, one element at a time. And then watch this very carefully. Step 3 is very unusual. So far, we've been counting electrons in pairs, lone pairs. Here with formal charge, they count individually. So dot by dot, you're going to be counting them with formal charge. We do that for every element in a compound, and then we can't do much. Formal charge is a way to compare possibilities. So I do that for every element in a compound for every possibility. And then I'm going to compare. And when I'm comparing, what I'm really hoping to find is a case where all the atoms get 0 as the answer. If that doesn't work, then I'm looking for getting negative ones on highly electronegative elements, elements close to fluorine. So fluorine, oxygen, chlorine, maybe nitrogen and sulfur. If they end up with negatives, that's pretty good. Or positives on elements far away from fluorine. That would be okay too. And numbers greater than 1, whether it's a positive or negative, aren't nearly as great as 1, because what's the best case scenario? 0. And the farther we get from 0, the not as probable that structure becomes for what nature's going to do. Okay, has everyone had enough time to write these down? Yeah? Okay. Almost there. Okay. Now, from the beginning, I've been saying formal charge is a way to compare possibilities. So it only works when we have more than one possibility. So 2 examples we're going to do. Our first examples with carbon dioxide, and I picked something easy to begin with. I could think of 3 ways to draw carbon dioxide. Now, we talked about this last week, but I want you to see how formal charge proves what I told you as kind of a guideline last week. So formal charge is a way to say for certain one way is better than another. So on your paper, you are going to want to draw the 3 different structures of carbon dioxide because we're going to have to compare all 3 to find the best situation. And I need to do formal charge for all 3. So I'm going to actually just make some little columns here to separate them on my screen. I'm going to do formal charge for every element on the left picture. And then formal charge for every element in the middle picture, and then formal charge for every element on the right. And then once we do it for all 3, we're going to have our comparison. Okay, most everyone's ready. The one on the left is what we would get if we didn't worry about sign-ops elements. So we'll see if that actually works out better than worrying about a multiple bond, but we can't compare till we do all three. However, we just get started with the valence electron. So notice first I'm starting on the oxygen. You take it one element at a time. What's oxygen's valence number? 6. How many bonds are touching that oxygen on the left there? How many bonds? Not meant to be a trick question. How many bonds are touching that oxygen? 1. So I'm going to subtract 1. Yeah, how many bonds? 1 bond right there. Yeah, I know it's Monday. How many electrons are touching that oxygen there? 1 at a time. Yeah, 6. So 1 bond, 6 electrons. 6 minus 1 minus 6 is a -1. Okay, that's not bad. Does that mean this is a good structure? We have no clue yet. We can't compare till we do all three. Let's look at the carbon now. So I'm looking at the carbon in the center. If it helps, I'm going to kind of circle it sort of there. And I've got 4 as the valence of carbon from the periodic table. How many bonds are touching that carbon? 2. Really weird question. How many lone pairs? Or sorry, how many electrons? 0. You can say 0. It's a valid number. 4 minus 2 is 2. And now I'm going to look at the oxygen on the right. Starts with 6 valence electrons. How many bonds? 1. How many electrons? 6. So it's also -1. Hey, that's pretty good. It all zeroes out. And, well, I do have a number 2 there, though. And but those negative ones are on electronegative elements. That's pretty good. So is this a good structure? You can't compare until you do all three. Be careful. Top number comes from the valence electrons right off periodic table like we've been doing. That's the only thing similar to what we've been doing. The rest of these steps are different. So please be very careful as you practice these to keep formal charge as a separate topic than what we've been doing. But it is a way to evaluate our work and make sure it's good. Okay, let's look at the center one. What's the valence of oxygen? 6. How many bonds are touching this oxygen? 2. How many electrons are touching this oxygen? It is 4. Okay, well, that's 0. Did I go too fast for anyone? Okay. Carbon is 4. How many bonds are touching it? 4 bonds. Any electrons? Nope. So 4 minus 4 is 0. And the oxygen on the right, well, since it looks like the one on the left, I'm not surprised that we end up with the same numbers. We get straight zeros. That's looking pretty good, because what was that first bullet point I gave you? Yeah, best case scenario, all zeros. But I'm not certain if that is best of the best until I've tried it all. So let's look at the one here on the right. So on the right, this oxygen, where's my, there it is 6. How many bonds? 1. How many electrons? 6. So this ended up being a -1 again. Well, that's not bad. It's a negative on an electronegative element. That works out really well. Let's check out that carbon. Carbon starts as 4. How many bonds? 4. No electrons, so that's 0. Hey, that works out really well. That's a good situation. And now let's look at this oxygen here on the right. It's 6, how many bonds? 3, how many electrons? 2. It's, wow, I was going to write 5. No, it's a positive 1. I'm going to write the positive just to stress it. You don't have to write positive signs. Ooh, I just put a positive number on a very electronegative element. That's not so great. So do we have an overall winner? Yes. We would say that this way of drawing carbon dioxide is the best. It goes along with those guidelines I gave you last time, but the guidelines I gave you last week are just that, guidelines. If we want proof that yes, it looks that way, formal charges are proof. But you have to compare all the possibilities and then decide of the end results which one's the best. We okay so far? Okay, let's try one more example of formal charge. And then we're going to preview the lab for next time. And then you can get into your assignment. I'll explain your assignment and you can get started on it. So again, I'm going to do both pictures before I compare. I'm actually giving you a moment to write down the pictures before we get started. No worries, I'll just stare at you awkwardly. Of course, at my age, everything I do is awkward anyway, so don't pay any attention to me. I could think of 2 ways to draw this structure, so I put them down. And last week I told you a guideline of I would expect it to be between synops elements. So with my guideline, I expected the one on the left to be the better picture. Do I have proof that that is the case? We're going to find out. Okay, so oxygen has 6 valence electrons. How many bonds are touching it? 2. How many electrons are touching it? 4. Yeah, count them individually. This is the only time we count them individually. So that's 0. Hey, that works out well. Nitrogen has a valence of 5. How many bonds? 3. How many lone pairs? Or, wow, I said that wrong. Don't say it that way. Sorry. How many electrons? 2. 2 electrons are touching it. So that's 0. And then chlorine. What's the valence of chlorine? 7 valence electrons. It's in group 7A. So 7 valence electrons. How many bonds are touching it? 1. How many electrons are touching it? 6. Hey, that works out to be 0. Hey, maybe my guideline wasn't full of hot air to begin with. Oh, but we don't know till we make a good comparison. So let's compare this one. If I can find where my pen is. Where'd my, oh, it's way up there. Okay, there it is. Oxygen is 6, how many bonds? 1. How many electrons? 6. What's my total there? -1. Hey, that's really not bad for oxygen. Let's look at nitrogen. What's the valence number for nitrogen? 5. Yeah, you look up, it's in group 5A. It's got 5. How many bonds are touching that nitrogen? 3. How many electrons are touching that nitrogen? 2. Okay, we got a 0 there. That's good. So let's look at chlorine. Chlorine has 7 valence electrons. How many bonds are touching it? 2. How many electrons are touching it? 4. That grand total is 1, a positive 1. I'm going to put a positive just to stress positive 1. That really is not awful, but let's compare. What's the best scenario? 0, 0, 0 or negative 1, 0, positive 1? 0, 0, 0 is definitely a better option. Now over here on the right, having oxygen, a negative 1, that's supposed to be an arrow. That's not bad. Oh, but chlorine is also very electronegative. It's the third most electronegative element. So it goes fluorine, oxygen, chlorine. Just letting you know. You don't need to memorize that or anything, just letting you know. And it has a positive number. Not a good situation to have a positive formal charge on a electronegative element. Now, if that was like hydrogen, far away from fluorine, a positive 1 would be okay. But on a very electronegative element, having a positive there is not a good situation at all. So that's how we're going to do formal charge. And in your practice, all I'm actually going to ask you to do is practice finding those numbers. I'm not going to ask you to find the numbers and then compare. I assume once you know the numbers, you'd be able to compare if I asked you to. But the practice you're going to be seeing is finding those numbers, and then there will be a drop-down menu, and you just tell me what the number is for each element. That's what I want to practice there. But before we get to your practice, I want to prelude our lab for Thursday, because Thursday is going to be a busy day. You're going to come in Thursday, and we're going to get the lab started right away, because it's a really interesting lab. We're going to have to get it started right away because it needs time to run. You're right. Thank you, thank you, thank you, Wednesday. I keep saying Thursday. I guess in my mind, I'm hoping it's Tuesday already. I don't know. Wednesday, we're going to do lab. Wednesday, you're going to come in. No, go back a slide. Yeah, Friday's a half day, but it's still an even day. And then you get off Monday, and then Tuesday will be an odd day. Crazy stuff. But makes for, you know, better than not having a half day, huh? Okay, let's see if I can make this work. So as I was saying, oh, it showed up over there. All right. Okay, if you'd please turn your attention to the screen. We're going to need, when you show up Wednesday and we start class, you're going to need to get the lab started right away. So then while we talk about intermolecular forces, the lab can be running. And then when we're done talking about the intermolecular forces, we're able to find the results of the lab. So I have a video here that's almost 11 minutes that's going to show you the steps of the lab so that it's easier to do if you've seen what to do. So please pay attention to the screen. And then after this, we will talk about your assignment and you'll have time to get to your assignment. So tomorrow you're going to be doing some paper chromatography, and I really enjoy doing paper chromatography because it is a simple yet very effective way to get some qualitative information about what's in a mixture. It's going to separate molecules based on how well they attract a movable phase versus a stationary phase. And we will have plenty of time in class to discuss that, but I want to get to how you actually start paper chromatography, because what you need to do as soon as you get to class and we get started is to set it up so it can develop as we discuss how it actually works. So you can imagine with paper chromatography, we need chromatography paper. This is a special paper, not unlike coffee filter paper, but it is cut to a big strip for us. And Sometimes the strips are wide, sometimes they're narrow, it doesn't really matter. But I'm going to start by making a starting line, and I want my starting line to be about 1 centimeter from the bottom, and check this out, I'm using pencil. Okay, and the reason I'm using pencil for my starting line, here you can kind of see it, the reason I'm using pencil for my starting line is I know that the pencil will not dissolve in my movable phase. That would be an issue. Then I would be separating what's in the pencil instead of, so don't use pen. If the pen were to separate, then you'd get pen interference with what you're trying to separate. Now also on the other side, so I put pencil mark there, on this side is my name. Okay, so I wrote my name on this side, get it? It says my name. Okay, literally. So I've got my name on this side, there it is, and I've got the pencil mark on this side as a starting mark. And I'm going to now place my sample mixture on my starting mark. So I have purple stuff, and you, of course, you will know in class what we're using. It's going to be a common everyday thing. But I'm going to take the toothpick that's soaking in my purple stuff, and I'm going to use the tip of the toothpick by holding it on the starting line to put a dot. And I'm going to re-dip, and I'm going to tap it once again. So notice I'm not tapping for long, but I wanted to try and get that 2-layer going on. So I got a good amount of purple stuff. You can see the purple stuff on my starting mark there. All right. Now that I've got the starting stuff on my, the purple on my starting mark, I'm going to size it up for the beaker. Notice the beaker is empty. I'm sizing it up for the beaker, and you could do this before you dot. It might even be better that way. But I want the bottom of the paper to just barely touch or even float slightly above the bottom of the beaker. So I'm going to wrap it around the pipe cleaner in such a way that it's going to hang barely touching or slightly above the bottom of the beaker, and then holding that in place up here with the paper clip. So your setup should look like this. And see how it is barely resting above the bottom of the beaker. So either barely touching or resting above. What you don't want to do is just ram the whole thing down into the bottom, because crumpled up at the bottom is going to do you no good at all. Notice the beaker's been dry so far. Okay, I'm going to now take my stationary phase out. This is my stationary phase, the paper, and I'm going to add my movable phase. With what we're going to separate, I know it dissolves in water, and when you realize what we're going to be using, you're like, well, duh, yeah, because we use water to mix it up. So I'm going to take water, about 25 milliliters of water, and that is stated in the lab, and I'm going to pour that in. Now I have my movable phase in the beaker. I have my stationary phase right here as the paper, and I'm going to lower the paper in slowly to where it dips into the water just barely. That's what I want. I want it to make contact with the water. I do not want the dot submerged in the water. If the dot is submerged in the water, then it will wash away and you won't get the results that you need to get. And we're actually going to sit here and watch it develop. I'm going to zoom in. You can actually already see some splitting, and it's just going to continue for a while. So if from this point in time you want to fast forward the video and watch it develop, I would recommend that. Just be sure you catch the very end as to what we do to finish it off. So hang out with the video going, and I'll let you know when we're ready to finish off. But you can already see how we are qualitatively separating. We're like, oh, in the purple was some pink stuff and some blue stuff. And of course, that's not shocking, because you're like, yeah, that's what mixes to make purple. But that is definitely what we are seeing. So we're going to watch this develop, and you may want to sit back and enjoy a cold Mountain Dew or something like that while you wait for it. This is the time in which we would be discussing how this works in class. So feel free to fast forward to almost the end and watch how we need to wrap this up at the very end.
Okay, so welcome back. If you were fast forwarding, hopefully you have stopped. I'm waving to be like, hey, pay attention. Okay. As you can see, even in this short time, we got our purple to separate into blue and red. And, you know, that is not surprising. But here's how we need to finish it off. We're going to get a piece of paper towel. And on our paper towel, we're going to place our wet chromatography paper. And I need to trace how far the water line got. So I'm going to, and I can use pen this time, I'm going to trace how far the water line got just by literally tracing the water line. You can use pencil too, doesn't matter. And then I also want to find the center of the color blobs. So there's like the center of my blue blob, and finding the center of my red blob, I feel it's kind of like right there.
So you will be doing these steps.
Now, if we waited longer, more and more of this red is going to be, you know, moving up and up and up. And so it would continue to separate them the longer we give them. But this is certainly plenty for our qualitative work right here. All right, so we have our solvent line marked. We have the center of our blue blob, center of our pink blob. What I need to do now is calculate a thing called an RF. And that is the distance from the start line to how far the center got, divided by the start line to how far the water line got. And since I have two colors, I need two RFs. I need an RF for the pink, and then up here I need an RF for the blue. So it would be the distance the blue dot there traveled compared to the distance divided by, that is, the distance that the water line traveled. And that's how we get this thing called an RF, resolution factor. And all an RF does is references for us how well we were able to separate these. So you can notice a big separation. So a little prelude for tomorrow. Since the pink did not move a lot, it must be more attracted to the stationary phase, the paper, than the mobile phase, the water. And the opposite, since the blue traveled a lot, it must be very well attracted to the movable phase, the water, and not so attracted to the stationary phase. And so we could do this for almost anything that's a mixture of things that we have a movable phase and a stationary phase for. There's lots and lots and lots and lots of types of chromatography. Each one uses a different stationary and different mobile phase because of the type of molecules you're separating. Now, before we end, I want to show you this one other thing. Earlier, I did paper chromatography for green food color, and you're like, well, if purple is, you know, red and blue mixed together, which kind of makes sense, green should be blue and yellow. Well, here is my green food color. It moved all the way up. And what I want to point out is this is actually, in this particular case, FDNC green number 3. That is what you know of as green food color. If you ever buy the boxes of food colors in the store and you squeeze out of the green bottle, this is what you're squeezing out. This is one molecule. It is not a mix of blue molecules and yellow molecules. There is no yellow molecule because it is just one molecule. Now, I'm not saying you could not mix blue and yellow and get green. Absolutely. But that's a blue molecule with a yellow molecule to make an appearance of green. This is a single green molecule. So this is the coolness, the power of paper chromatography. It told me this is not a mixture. This is a pure compound. This is one green molecule because I got no other separation. If it was a mixture, then I would easily see a blue dot and a yellow dot, and I would do the same RF factors I did over here for a purple. Okay, so that's paper chromatography, and that's what you need to do tomorrow. So you're going to set it up tomorrow with your assigned color. I'll assign you a color. You don't get to pick. And while it's doing this dissolving thing and the water's moving up the paper, we will discuss.
Okay, so where'd it go? Right here. Okay, so I will send a link to that video and remind tomorrow so you can watch it and have it fresh in your mind for Thursday. Because again, Thursday, when you come in this room, the expectation is you're getting started on setting that up right away. And then as we wait for it to go up the paper, we will talk about intermolecular forces. Everyone has a new practice in Canvas. So you go to the home page, you click on January 1st, 11th, and 12th, and the practice is there. It's 2 halves today. The first half is the regular things you've been doing, but now I'm going to ask you hybridization because you have that on your chart. So there'll be a new drop-down menu for hybridization. The second half is formal charge. And as I already said, when I ask you formal charge, I'm going to give you just one compound. I'm just asking you to practice getting the numbers for each of those elements. You'll drop down the menus and get the numbers for each of those elements. And that's all I'm going to ask you to be able to do with formal charge. Later on, I might ask you to compare and pick one which is best. I think you all mastered that easily. I want to be sure you got the steps for getting the numbers. That could be the tricky part. So we have a good half an hour, a little more left in class. That's what we're up to. Get into Canvas, get that practice going. Online students, if you hang out, you're welcome to ask me questions if you run into them. If you have to close down Zoom to get to Canvas, I understand, and I wish you a great day. In-class students, feel free to pull out your Chromebooks and get started. And if anyone in the classroom needs a Chromebook, just let me know. I will pass them out.